Hi everyone. This video is going to go through the next section of our course, which is 3.2, which touches on the wave-particle duality as part of our focus on light. So here we have our science understandings that will be covered today. So just take a moment to have a read through and make sure that you check back in with these science understandings at the end of the video to make sure that you have a really good understanding of what's being covered. So the first thing we're going to have a look at today is what is a photon? Now, when light interacts with matter, it does so in a manner that cannot be described in terms of wave motion. And up until now, when we've been looking at light and talking about how it interferes and interacts, we've described it as a wave. Now, interference and diffraction are both wave properties or wave characteristics. Now, other phenomena of light require alternative explanations. So it reached a phase where our understanding of light moving and interacting as a wave wasn't quite cutting it as an explanation of what we were seeing in some really strange experiments, and we'll investigate that now. So some of the requirements that we need to have a really good understanding of about photons. Photons are considered discrete packets of energy, and all of these will be unpacked a little bit later on as well. So each photon has an energy that can be calculated really simply using this formula here, and it's E is equal to hf, and we'll unpack that as well. And we also have to know that a photon can have momentum, and we'll have an understanding of what that means shortly too. And it can be quite a strange concept. We introduce a new constant called h, which is Planck's constant, and then recover in frequency and wavelength. So we use our wave equation quite a lot as well when we're looking at the speed of light and the frequency and the wavelength and how they interact. So some background information about one of the things that made physicists start to think that maybe light didn't always behave as a wave is our double slit experiment. And when we have a look through a Young's interferometer, this top section here sort of shows what kind of interference pattern we see. And if we look at it through a sodium vapor lamp, which traditionally glows bright orange, we'll see really bright orange fringes and really dark black fringes. And the interesting thing to note is if we set up the very same experiment in a dark room and only let really low levels of light to actually travel through the double slit, what starts to happen is we get a buildup of dots happening on the screen, and you can see those in the two images below. All right, so why is this important? Well, we know that traditionally when we look through the interferometer, we see this and we see this straight away, and there's nothing really unusual about that. It's all very much explained by the interference of the waves and forming the characteristic interference pattern that we see there. But these dots were really strange because if they changed the film and repeated the experiment, then the dots were hitting in different places. And so what would happen is if we kept repeating this over and over and over and combining the image, then it would start to build up the top image that we're seeing there. So it wasn't straight away happening that this, figure 11.2 was occurring. It was building up over time when we're using really low levels of light. And as you can see, this image is represented in the second and third image there, just do not reflect our understanding of light interfering as a wave. So it's this build-up of the tiny dots that formulate the top image that we're used to seeing. When we see an image straight away without a gradual build-up, it looks like that straight away. But you can start to imagine that it's a very strange phenomenon, and it wasn't able to be explained by our understanding of light moving and interacting as a wave. So something else must have to be happening. So what was happening? Well, the dots represent the minimum unit or quantum of energy in which light arrives. So these minimum quanta of energy are called photons. They're like individual packets of traveling energy, and each one of those is represented by the dot on the film. So it's this build-up of photons hitting the film over time that build up to create the more familiar wave-like interference pattern that we saw in that top image. So calculating the energy of a photon, this tiny packet. The energy of a photon is given by this equation. E is equal to h multiplied by f. Now h is constant. It's called Planck's constant, and it's represented there 6.63 times 10 to the negative 34 joules. So it's a very, very, very tiny amount. Now frequency represents the frequency of light from a particular wavelength, and E is just our friend's energy. So energy is measured in joules. So this next slide is not accessible. We don't have to be able to derive the following formula, but basically to give you some background information on how we work out the momentum of a photon, we have our wave equation here. So frequency is equal to the speed divided by the wavelength of the wave. If we substitute that into a previous equation, we get an interim one. So we get the energy is equal to hc over lambda. And bear with me as I go through the next step of this process. All right, so when we have a look at this little guy called a photon, there's some things we need to understand. So when light interacts with matter, it behaves like a particle or a photon. Now, one of the fundamental principles of the interaction of particles is the conservation of momentum. And every time we've talked about momentum up until now, we've referred to momentum as being a property of moving objects that have a particular mass and velocity. So P for momentum is equal to m times v. Now, an American scientist, Arthur Compton, experimentally found that when a photon hit an electron, they acted in such a way that the total momentum before and after the collision was the same. So momentum was conserved. So you can almost imagine our more familiar momentum scenario with the air hockey pucks moving on an air hockey table, and one of the incoming air hockey pucks representing the photon striking a second puck, which would represent the electron. Now, the concept of momentum was developed for particles with both mass and velocity being really important. Now, we have our formula, P is equal to mv, so both mass and velocity are pivotal. So how do we assign momentum to a photon? And really, does light have a mass? And that's a really interesting question. So again, I'm just reiterating that this part of our course is not accessible, but it is really nice background information to have. So the answer from our question of does light have mass comes from Einstein's theory of relativity. So E is equal to mc squared. Now we have E on one side of our equation and we have mass on the other. So that implies that both mass and energy are interconvertible. If one decreases or is lost, then it can be re-represented as the other. So in terms of his equation, matter can be destroyed and energy created, which sounds counterintuitive of our knowledge of physics up until now. So although photons are constantly moving and have no rest mass, the energy of a photon can be equated and something called a relativistic mass found. So what it would have, or what its mass would be if it did happen to be at rest. Although we know that can't happen because they're constantly moving. So for the purpose of mathematics and trying to equate formula, we assign it something called a relativistic mass. So to do that, and again, not accessible, but interesting background information to have, is we have our two energy formulas. So E is equal to HF, and our relativity formula, E is equal to mc. So we can equate those, and they haven't done a really good job on this particular slide, but we can see there that the HF comes down to here, and the mc comes from there, and we can equate the two of them. Now from our previous slide, we know that frequency is equal to hc over lambda, which is what gets plugged in over here instead of frequency. So once we have that, we can cancel out our c's across, and you can see what happens. It gets distributed, and we're left with this at the bottom, a relativistic mass formula. So mass is equal to h, which is Planck's constant, divided by the wavelength of light multiplied by c, the speed of light. Okay, so it was important to get m on its own, as you see from the previous equation up here, because we know our conventional understanding of momentum is P is equal to mv. So if we substitute our new formula instead of m into our momentum equation, we have P is equal to what we did have for m, all right, and then v, when we're talking about light, is always c, or the speed of light. So there we can see we've got this new equation that P is equal to h over lambda c times c, and the c's cancel out, and what we're left with is this red box equation at the bottom, which is a formula for the momentum of a photon. So we can actually calculate the momentum of a photon simply using Planck's constant and the wavelength of the light we're using. So a photon, back to our important points, has both energy, which we can calculate, and it has momentum. So here's our old friend, the electromagnetic radiation spectrum. So down the larger wavelength end, so if I've got my wavelength is increasing down here where I've got radio waves, if we have a big wavelength, it means that our frequency, which is given by 1 divided by the wavelength, if the wavelength is big, if this number here is large, then our frequency is going to be small. So wavelength big equals frequency small down that end of the spectrum. As we start increasing, going along our spectrum and the wavelength starts getting shorter, so if we start going, I look down the other end down here, if frequency is equal to 1 over wavelength and our wavelength is getting smaller, so here we have a small wavelength variable lambda, but it'll do, is equal going down, it's going to mean that the frequency is getting a lot bigger. So here we've got, if we look at gamma rays, where they're in the order of times 10 to the negative 12 or negative 14 meter wavelength. So if you've got a really tiny wavelength value, then your frequency is going to be massive. And we know that our energy formula, E is equal to H times F. So if we use that as a basis, if our F is going to be small, so here we have a small f down the bigger wavelength end of our spectrum, so radio waves, microwaves. If our f is small, then our E is going to be small. And conversely, if we're down the other end of our spectrum and we've got tiny wavelengths, then our frequency is going to be huge. Therefore, the energy is going to be huge. So you see here, I've got a highlighter. The photon energy decreases when we have a large wavelength, and the photon energy increases when we have a tiny wavelength. And therefore, we have our other new formula as well, which was for momentum. And momentum was equal to frequency divided by, I've lied, it's not frequency, Planck's constant, h divided by wavelength. So it's inversely proportional to the length of the wavelength. So that means, if I've got a colour, yes, that momentum is going to increase as the wavelength gets tinier. And down the other end, down microwaves and radio waves, when we have a bigger wavelength, it's going to have less momentum. So the next part we're going to go through is something called the photoelectric effect. So at the start of the 20th century, physicists thought they had a pretty good handle on light and how it behaved and how it interacted. We had James Clerk Maxwell, who had written a really complex set of equations that described the behavior of light really well. And then using these equations, we had Heinrich Hertz, who was able to build on the work of Maxwell and actually use his equations to discover radio waves. So when Maxwell was, when he put out his equations, he basically wrote a set of assumptions that meant this is what should happen at all levels of the electromagnetic radiation spectrum. And using that, Hertz was able to then discover radio waves exactly where they were predicted to be. The only issue with all of this was one thing, and that was called the photoelectric effect. So the photoelectric effect is a phenomenon where a type of metal is illuminated with a particular frequency of light. And if the light that's shining on that metal is of a high enough frequency, what we see is electrons being emitted from the surface of that metal. And this phenomenon is called the photoelectric effect. So this is another image just trying to demonstrate the photoelectric effect. So if we have atoms that make up the surface of our metal, so here we have some 1, 2, 3, 4, 5, 6 protons in the nucleus, so we have carbon. Not a great example of the photoelectric effect, but if we had a carbon atoms making up a particular metal, we have protons and neutrons that make up the nucleus of our atom, and then buzzing around the outside we have our electrons. So electrons are negatively charged and our protons are positively charged. So there's a force of electrostatic attraction that holds the electrons into the nucleus. Now, what we see here is our incident photon, this guy up here. And what's important to know about electrons and how they're configured is that the inner shell electrons, so these guys here, are held really, really strongly by the nucleus by those electrostatic forces of attraction. The further and further away we get from the nucleus, so this guy here, he's held more loosely or not as strongly to the nucleus. So that's an important point to note. And then we have our incident photon, this little guy up here. What happens is the incident photon, if he has a high enough frequency, he's going to come along and interact with our electron. And basically the momentum or energy from the incident photon is transferred to the electron, and the electron is emitted from the surface of the metal. It's almost like it's knocked out. Now, to be able to do this, the energy of the photon needs to be greater than the electrostatic forces of attraction to the nucleus. So it needs to be able to give it enough energy to break free and pop out of the metal surface. So to observe the photoelectric effect, we use something called a photoelectric cell, and this is a diagram of a photoelectric cell. And basically it consists of a curved metal cathode, and that's this guy at C over here. And it's called the emitter because it's the thing that's going to be emitting the electrons. And we also have something called an anode, which we can see at point A there. So that long piece there is called the anode. And that's going to be the detector. And all of these are placed inside a evacuated glass jar or tube. Now, to be able to measure what's happening here, the rest of that, well, the photoelectric cell needs to be placed into a circuit. And that way we can actually use a really sensitive ammeter down here as part of our circuit to actually detect whether or not we have a flow of current. So you remember that current is a flow of negative charge, which is made up of electrons. So as soon as we get, you can see up, where's a different color, our light being shone on the cathode or our emitter, if it's of a sufficiently high frequency, which we'll talk about in a moment, we should start seeing some electrons pop out and start being sprayed from the emitter. If they've got enough energy, they'll make it across that little gap there and be picked up by our detector. Once they're picked up by the detector, we should see a flow of negative charge down through the conducting wires, passing through our ammeter, which should read as a current. So as soon as we have light shining on that cathode, we should see an emission of electrons, which starts up our reading of our current, and we should see a value of current. And that would show us that the photoelectric effect is actually happening. So here we have in more detail. So when light of sufficiently high energy or electromagnetic radiation is incident, which means hitting the matter, and in this case the matter is referring to our cathode or our emitter, that's this guy over here, it can give electrons high enough energy to actually overcome those electrostatic forces of attraction to the nucleus of their atoms, and they can leave the material. Once they leave the material and are sprayed out, that effect is called, or the phenomenon is called the photoelectric effect. And as I said, we can pick that reading up here with the ammeter. Okay, so there's some important observations of the photoelectric effect. Number one is that the electrons are emitted instantaneously. As soon as the first photons strike the surface of the metal, the electrons will start to pop out. As long as they've got enough energy to be released from their metal atoms. And this is really important. It's regardless of the intensity of the light, and we'll talk about that a little bit more in a moment. Number two, that there is a minimum frequency or F0 or F0 below which no electrons are ejected. Now this is called the threshold frequency, and it varies with the type of material. So the image that we have below, we've got a sample of metal, and it's being struck in with different frequencies or wavelengths of light. So over in this example, we've got red light striking the surface of the material, and we can see that no electrons are being emitted. So that tells us that that red light, which has a very particular wavelength and therefore a frequency, which we can calculate the energy of that red light, E is equal to hf. The energy that it's giving or trying to strike those electrons with obviously isn't enough to break them free of the electrostatic forces of attraction holding them into their atoms. In the next diagram here, we have green light. Now, remembering our visible spectrum of light, we have Roy, G, Viv. So G is in the middle, green. So it's going to have a little bit shorter wavelength and therefore a higher frequency. And we look up here, higher frequency means more energy. And what we notice is we can see that we have 3 little electrons that have been popped out from that metal. So that tells us that green light must have enough energy to start releasing or emitting electrons from that particular metal. Now, as we move forward, here we have purple or violet light. And again, violet has an even smaller wavelength, which we can see by the waves hitting that metal. So it's got a smaller wavelength. Again, it has a higher frequency. Higher frequency equals higher energy. And so for this particular metal, some of the energy of the incident photon is going to be used up in liberating the electron from the atom. Any additional or leftover energy is transferred into kinetic energy. So in the middle diagram, these electrons are moving off with some kinetic energy. And because the energy of the incident purple light over in this diagram was higher, you can see that these electrons are moving off with even more kinetic energy because some of the energy was used up for them to break free of their atom, and then the remainder of the energy was transferred to kinetic energy. So those electrons are moving away from the surface of the metal with much higher velocities than the ones that were hit with the green light. All right, so here's where we talk a bit more about intensity. So number 3, intensity of the light. And when we're talking about intensity of light, all we're talking about is more photons. So intensity refers to how bright the light is. So if we have, let's say, a red light, because I'm writing in red pen, we have light of the wavelength for red color. And if it's a really like a dim light, we still have wavelength that's exactly the same. Therefore, each photon is going to have the same energy. Now, intensity just means how many photons of that light are actually being emitted. So the more bright the light, the more packets of photons that are actually coming or being incident in that scenario. So every one of those photons still has exactly the same energy because of our equation. E is equal to H, frequency, terrible writing, which means that for the particular frequency of red light, every photon is going to have the same amount of energy. So back to our point there, 3, intensity or brightness of the light affects the number of electrons emitted, not the energy of those electrons. And when they're talking about energy, they're talking about kinetic or how quickly they're actually moving away from the surface of the metal. Now, if there are more photons, there's a greater chance that they're going to interact with an electron, and therefore that explains why more electrons will be emitted. Now, these two factors are proportional, which means that a larger current is detected by our little ammeter in the circuit when the intensity of the light is increased. And again, the reason, if the intensity is higher, we've got more photons being available to interact with electrons and pop them out of the metal, which means that we'll have a larger current detected, but not energy, because remember, E is equal to HF. So for every photon of red light, they all have exactly the same energy. Moving on to number 4, electrons that are emitted from the metal have a range of kinetic energies. And we kind of touched on this already. Now, these range from 0 to a maximum. So we mentioned before that every atom holds onto its electrons differently. Now, the inner shell electrons that are closest to the nucleus are going to be held onto more strongly or have a greater amount of electrostatic attraction. The ones that are right around the edges, so the furthest distance from the nucleus, are going to be held on more loosely. Now, those ones will have to be given less energy to actually free them from the nucleus. And the ones, if we're wanting to free an electron that's really close to the nucleus, we're going to have to provide it with much more energy to actually break away. So depending on where in the metal the electron has come from, a lot of the incident photon's energy will be taken up to liberate it from the electron, and the remainder will be transferred into kinetic energy. So what happens is when the electrons are freed, they might be given just the right amount of energy from the photon to be freed, but if all of it's taken up in the freedom of the electron, none of it is available to be transferred into kinetic energy. So it kind of just sits there. So it would have a zero kinetic energy, and that's what this one's talking about, zero. If the electron has come from right outside of the atom and it only required a tiny amount of energy to be freed, then all of the additional energy from the incident photon will be transferred to kinetic energy, and that one will move off with quite a huge amount of kinetic energy and move off quite quickly. So we end up with this huge range of kinetic energies being emitted by the electron. The electrons that are emitted having a huge range of kinetic energies. So Einstein had a very particular explanation about what was happening in the photoelectric effect. So he postulated that light does not consist of continuous waves, that it consists of packets called photons, and that each photon was able to have an energy, which we've talked about already. So energy is equal to hf, where h is Planck's constant. And he also said that photons have some wave properties and some particle properties depending on the situation. And this was a really novel idea because, as I said, at that point in time, everyone thought they knew that light acted as a wave, or light was a wave. He also said that each photon will be absorbed by only one single electron. So each incident photon will interact and knock out and pop out one single electron from the metal. Now, because this was such a novel idea and no one had thought of it, and it actually changed the face of physics quite a lot, Einstein won a Nobel Prize in 1921 for his explanation of what's actually happening in the photoelectric effect, which was amazing. Now, this is a representation of an energy level diagram for a particular type of metal. So here we're looking at copper metal, and what we're seeing here is basically the amount of energy required to be given to electrons for them to be able to be released from the metal. So we call it the work function of a metal is of a material is the minimum energy required to remove an electron. So that's called the work function. Electrons are bound to the material and they require energy to make them leave. So therefore they have negative energies. So in order to us to remove an electron, its energy level has to be raised to zero. If the incident photon has more energy than that, it will be able to convert the additional energy into kinetic energy. So let's expand on Einstein's explanation a little bit. So about point one, if photons behave like a particle, when an electron in the metal absorbs the energy of the photon, then the transfer of energy is immediate. So what we see is that the electrons are emitted instantaneously as long as the photons that are arriving and striking the metal have an energy that is higher than the work function of the metal. And point number two, if the frequency of the light is reduced, it means that the energy is also reduced, because we know that our equation is E is equal to HF, which means that if the frequency goes down, then the energy is also going to go down. If this energy drops below the work function of that particular metal, then the incident light or the incident photons don't have enough energy to actually release those electrons from the electrostatic forces of attraction that is holding them onto their metal atoms. So what we actually see is that no electrons would be emitted if the frequency wasn't high enough. So this is called the threshold frequency of the metal, as we've touched on already, which is noted as frequency 0 or frequency 0. The work function is basically a measure of energy, or how much work needs to be done to free the electron from a particular metal. So the work function is specific to each metal, and it can be calculated by h times frequency 0. Einstein's explanation of the third observation was around the intensity or brightness of the light. So the intensity, remember when we're talking about light, refers to how bright or dull it is, which means how many different how many photons are making up that light. Now, the brightness of the light is directly proportional to the number of photons, which means if there are more photons available to be absorbed by the electrons in the metal, then more of them are going to absorb them and pop out. So this is what we see. More electrons are emitted with more intense light because essentially there are more photons and more opportunity for them to be absorbed. His explanation of the last observation was around the conservation of energy. So if using the law of conservation of energy, part of the energy of the incident photon is used up in releasing the electron from those electrostatic forces of attraction that hold each electron to its nucleus. Anything that's left over becomes kinetic energy of the electron after it's released. So since electrons that are deeper in the metal require more energy to be released, the amount of kinetic energy that's available afterwards actually varies. So electrons from the surface are emitted with greater kinetic energy than those that were deeper within the metal. And the reason for this is because they only required a little bit of that incident photon energy to be released, and everything that was left over, which is quite a lot, is transformed into kinetic energy. So this means that electrons are emitted with a range of kinetic energies up to a maximum value. Now, increasing the frequency of the incident light, because remember that the energy of the incident light is equal to h times f. If we increase the frequency, they get more energy. So therefore, the maximum kinetic energy of the emitted electrons also increases. To work out the maximum kinetic energy of the electrons once they leave the surface of the metal, we have this equation here, which is sometimes referred to as Einstein's photoelectric equation. And it states that the maximum kinetic energy of the released electron can be found by Planck's constant multiplied by the frequency of the light minus the work function of the particular metal. And if we compare this to the equation of a straight line, we can see some really interesting similarities. So h would be the gradient or the slope of the line. We have frequency, which would give us the x variable on the graph, x-intercept, and the w is our y-intercept on the graph. And it looks really interesting when we have a look at what a graph would look like. So here we see two similar graphs that are both graphing the maximum kinetic energy of the released electrons on the y-axis versus the frequency of the incident light that released the electrons on the x-axis. And what we see is some really interesting features. All of the slopes of the line, of the lines on the graphs, are identical. And what the slope should give us for all of those lines is the slope should equal h, which is Planck's constant. Depending on what sort of metal we were using as a cathode, or which kind of metal the electrons were being released from, the lines will be in different positions as indicated here. But when we analyze a bit further the parts of the graph, so here we see where it hits the x-axis should be the threshold frequency for each of those metals. Where it hits the y-intercept, the y-intercept will show us what the work function of that metal is, which means how much energy needs to be put in to be able to emit electrons. So here we see this distance here will give us an energy value because this is a graph of Kmax. So the distance there will tell us which value of energy needs to be put in to release an electron from that metal. What we see here is that a different type of metal has exactly the same slope. It has a particular a threshold frequency for that metal, and it also has a very specific work function for that metal. So if we're looking at the graph on the left, we can infer that metal 2 requires a greater amount of energy of incident photons to actually release electrons because its work function is a lot further down on our y-axis. One of the things we need to be able to do is to talk through an experiment that is able to calculate the maximum energy of emitted electrons. And this can be determined experimentally using a photoelectric cell as indicated here. So the cell is placed in a circuit, and white light that has been passed through a filter or light of a single frequency is used to illuminate our cathode. So the next thing that has to happen, so here was our cathode, remember that was our emitter, and we have this guy here, which is our anode, which is our detector. So as the electromagnetic radiation illuminates the cathode or the target metal, we should see some electrons being emitted and being collected on our anode. What we also need to have is the rest of it in a circuit, and there's a couple of important things. So here we have our voltage or our potential difference. It may be provided by a battery or a power pack, but we need to be able to put in or apply a potential difference. We also need to make sure we have an ammeter in our circuit because that will indicate whether or not the electrons are reaching the anode, because we will see that registered as a current. So once we've got it set up, we start to apply a potential difference to our circuit. And what that does is we want our negative, if we're attaching it to a battery, or we want to make sure that our negative connector is heading to our anode as indicated in the diagram. So when we apply the potential difference, it produces an electric field which repels the electrons, because if we put the negative end here, it means that our anode is going to become negative. And if our electrons are jumping across here to our anode and electrons are negative, they're going to be repelled by our increasingly more negative anode, which as we start increasing the potential difference, it's going to stop them from reaching the anode because it will repel those electrons. Now the potential difference is increased, making the anode increasingly more negative. So this means that fewer electrons have enough kinetic energy to overcome the repulsive force and actually reach it. So when no more electrons reach the anode, the current, as measured by our ammeter in the circuit, will actually drop to zero. And this particular point is referred to as the stopping voltage. When the stopping voltage is achieved, the work done by the electric field matches the maximum kinetic energy of the emitted electrons. So only the fastest moving or the highest or most energetic electrons were able to reach it before, and at that very particular stopping voltage, they're no longer able to do that. So what we can say is that the stopping voltage must equal the amount of work being done there. And here we have an equation that W, or the work done by the electric field, must equal the maximum kinetic energy. So here we have work, which must equal the stopping voltage, which must equal the maximum kinetic energy of the electrons. So we can equate the parts of that are relevant to us, which means that the maximum kinetic energy of those electrons can be found by multiplying the charge on a single electron by the stopping voltage that we've just calculated. Once we've done this, we can then change the color of the filter or change the color of the light and use that to work out a new stopping voltage and calculate the E or the maximum kinetic energy for other frequencies of incident light. Once we've done this for various frequencies of incident light, we can actually plot a graph of our maximum kinetic energy against the frequencies that we used. Once we do this, we can see that familiar shape that we've already investigated previously. So we have H, which should be the slope of the graph. Where it hits the x-intercept should be the frequency naught, or the threshold frequency of the metal, or of the light required for that metal, and W, or the work function, will be able to be found when we investigate the y-intercept of the graph.